Chriselda. I'm a PhD student based at Cambridge. And today I'll be talking about my work with collaborators Emmanuel Hartmann and Thomas Needham, which is conic formulations of transport metrics for unbalanced measure networks and hypernetworks. What do I mean by this? So the motivation actually started off with data sets which are intrinsically heterogeneous, and we want to sort of match these, right? For instance, stream networks, road networks, biological networks like gene regulation, or like even social network, right? Optimal transport is an ideal tool for this because we want to match distributions or match heterogeneous structures, data sets, and in particular, we're interested in Gromov-Wasserstein, right? So the idea is you have two different metric measure spaces, and we want to sort of compare them. My P Gromov-Wasserstein for P less than infinity is like an LP norm of the difference between the underlying metrics, like dx minus dy. A well-known result is if we have the same topological space, we can sort of bound our Gromov-Wasserstein with just the normal Wasserstein distance. Okay, so this is an interesting definition. So I'm kind of trying to generalize Gromov-Wasserstein beyond metric measure spaces to graph kind of setting. So I'm looking for measure networks, right? So what do I mean by this? So let me take nx. Here, x are the nodes of my graph, and eta x is an arbitrary weight function. It's basically the edge which connects the two nodes, right? And it's also a very generalized arbitrary weight function. For instance, heat kernels, adjacency matrices. And then mu x is my probability measure. So the Gromov-Wasserstein for measure networks is again LP norm of the difference, but here instead of the underlying metric, it's going to be my weight function, eta x minus eta y. Okay, so Gromov-Wasserstein is very interesting. It has a lot of applications, particularly biology. So here you can see that we're kind of trying to match the genes to the proteins and see how they sort of align with each other, right? So you have a collection of cells and you want to match both of these. But of course, there's a lot of caveats in the fact that GW distance requires probability measures which are balanced in some way, and they're not robust to outliers. So that's the motivation problem. And to deal with this or to circumvent this, I'm kind of introducing a conic Gromov-Wasserstein. So there are two ingredients for this recipe. My first definition is very general. It's on a metric space. So what we're doing is we're lifting from a space x to space x times r. So we have a spatial coordinate, and then I'm also adding a mass variable to it. So that kind of handles the discrepancy in the mass. So I'm dealing with unbalanced probability measures, right? So that leads to x comma r, where r and s are my radial coordinates, right? And if you see, my distance is now 4 delta squared, delta being some parameter, r squared plus s squared. So that basically captures the discrepancy in mass between the two probability measures. And then, of course, I have the warping functional d of x comma y. So this is for a metric space. That's my first ingredient. The second one is semi-coupling. So this is, again, a generalized notion of couplings where your projections are only fixed or like equal to just one of the marginals. So this allows for creation and destruction of mass, some sort of flexibility, right? Given these two conditions, so my semi-couplings here are gamma naught and gamma 1 respect to some dominating measure gamma. So I have my cost function. I also have what I'm integrating with. So this is what we have introduced. It's called the Gromov-Wasserstein for measure networks with respect to our semi-coupling is gamma naught and gamma 1. So here, my x and y would be replaced with my weight functions eta x, eta y, and my radial coordinates r and s will be replaced with my Redon-Nikodym derivative with respect to my semi-couplings. So this gives a notion of Gromov-Wasserstein, which also captures unbalance in measures. Interesting theoretical guarantees. I'm very briefly running through some of them. So the first is like a metric sandwich. So it kind of gives you a nice link between what we know in OT, which is the Hillingham-Torbich, or like the Wasserstein-Fischer, which is also called as unbalanced optimal transport, and Gromov-Wasserstein for the measure networks, what we know. The second one is my favorite, which is I always like some consistency results. So I said about this delta parameter. So we tend delta infinity and give some variational convergence in the notion of gamma convergence. We can show that the conic Gromov-Wasserstein converges to like Gromov-Wasserstein metric. And then some linear scaling, some bounds. And the last bit is we quantify that CGW is robust outliers. We give some quantitative bounds and also a counterexample why GW does not sort of behave well. And some final numerical experiment, just one of them. So this is a very simple example, just the problem of classification of M-list digits. I have 1 and 7, I perturb it slightly, and then to get like CGW on this and compare with the KNN graph. And you can see that I'm kind of benchmarking it in relative to like a GW distance, and the test error for CGW is much lower in comparison to like the GW. So basically, CGW performs relatively better than GW. The fact that's also robust to outliers is like a proof here. Thank you.